Hello everyone, welcome to another lecture for drug delivery principles in engineering. Just a quick recap of what we have done so far. So, previously we had learned about what is drug delivery, how are the drugs distributed in the body, so essentially their pharmacokinetics. Now, this was followed by a little bit of discussion on prodrugs as well as some polymers. So, we are going to just quickly recap on what we did in the last class in particular. So, we talked about prodrugs, nearly 10% of all the drugs in the market are prodrugs. We also talked about controlled release and long circulation advantages. So, why would you want the drugs to be prolongedly released in the body? So, essentially instead of having a traditional drug delivery system where you have to give high dose, so that reaches toxicity and then comes down, we want more to be stable in this therapeutic window. And then finally, we talked a little bit about what polymers are and what are the different types and all, and we are going to continue our discussion on polymers today. So, first of all, how are polymers synthesized? So, simply speaking, it is essentially individual monomer molecules come together and are covalently linked by various chemical reactions to produce variety of polymer molecules. So, this is a very simple definition there. So, essentially bringing in monomers and combining them chemically to get different polymers. So, there are various classifications in way in which the polymers are synthesized. A traditional classification that has been known in the literature is Carothers classification, and it is subdivided into two different types of polymerization. One is addition and another is condensation. In addition polymerization, you essentially have each repeat unit has the same number of atoms as the monomers. So, essentially they add without releasing any other molecule that is not the part of the polymer. However, in condensation polymerizations, you have less number of atoms in the polymer than the individual monomers, because typically the reactions involve release of water or acid or something else as a reaction product. This is again, as I said, Carothers is a very traditional classification, and the modern classification is based on how the reaction occurs. So, in this way it is again subdivided into two different classification. One is step polymerization and another is chain polymerization. So, we are going to talk about both of them as we go along in these slides. So, talking about step polymerization, in this process the polymer chains are essentially built up in a stepwise fashion, and this could be the random union of individual monomer molecules. So, essentially if we look at the reaction here, so you have a dimer being formed by combining of two monomers, a trimer is formed again by combining of a dimer to a monomer, but then from there on forward there are several ways that this can happen. So, a tetramer can form either by combining two dimers or by combining a trimer with a monomer, and similarly the possibilities increase further as you go along. So, it is essentially just a random union of monomer molecules which are combining. You can get a linear polymerization. This could include both the polycondensation or the addition polymerization, or this could be non-linear, in which they might be, instead of combining linearly, they might be combining in many multiple places, essentially creating a network of polymerization. So, what is the effect of functional group number on this? So, let us consider this chemical reaction. So, we have an acid reacting with an alcohol to give an ester group and also releasing water. So, obviously since there is a release of water, this is a condensation reaction. The important thing to note is that acetic acid and ethyl alcohol, which are being used here as monomers, they both have one functional group each. So, let us say that this reaction has happened, there is really no functional group left in the product that is formed. Given that there is no functional group in this product, the resulting molecule cannot go for the reaction. So, no polymerization will further happen. So, essentially all you have done is a simple reaction making a small molecule which is essentially not a polymer. So, what does this tell us? This tells us that for the polymerizations to happen, we need at least two functional groups on each of the monomer. So, an example here is the terephthalic acid with ethylene alcohol. So, in this case you have groups which contain both the acid has two different acids two different COH group, and then the ethyl alcohol again has 2 different OH group. So, in this way whatever the product is formed, even though you have used 2 of the functional groups, one each on the monomers, there are still 2 more functional groups available on the resulting product for it to further continue to react. So, quick thing here is what will happen if you have more than 2 functional groups in your monomer. Any guesses that you may have? So, I will give you a moment to think about that. So, as most of you might have guessed it already, if you have more than 2 functional groups, it can essentially lead to branch. So, you can have a situation in which you have a group here, a group here. If there is only 2, then essentially it can only grow linearly, but however, if there is another group on the monomer which is here, it can not only grow linearly, it will also grow in branches, leading to a complex network, essentially leading to a lot of branches in the polymer. So, some more examples of linear step polymerization. So, now we are only talking about linear. This also is examples of polycondensation. So, it means that it will result in elimination of small molecules. So, here is one example which we have already used in the previous slide, which is diacids reacting with dialcohols. They are typically rarely used, they do not have very good reactivity, however, they are used, and essentially you will have release of water molecule as well as forming of the polymer. Another reaction is dichlorides with dialcohols. This is more energetically favorable because the chloride is a good reactive group, and so you will essentially get a very efficient reaction in such cases, but in this case as it is a polycondensation reaction, you will have a small HCl molecule being released. And then alternatively you can have polyesters can also be made from single monomers. So, it does not have to be 2 different monomers, you can have a single monomer containing both the hydroxyl as well as the carboxyl group, and then they can react within the same monomers to form a polymer. Again some more examples here. So, this time we are talking about synthesis of polyamides. Do you know where the polyamides are seen in our body? Yes, if you are familiar with proteins, all proteins are essentially nothing but polyamides, and what it is a reaction of carboxyl group with an amine group. So, it could be something where 2 carboxyls on one monomer are present and 2 amines on another monomer are present, and they will react to form this amide bond, which is a CONH bond. So, essentially this is an amide bond, and this will be the reaction that will happen. Another example here is synthesis of polyanhydrides. So, this is reaction of 2 different acids with each other. So, this could be that you have a monomer R1 containing 2 different acids, and this will essentially react with itself to form this anhydride group, which is again represented as this group, and this essentially is an anhydride group, and you can have a polymerization happening like this as well. And then again there are lots of variation. Another example here is synthesis of polyethers, and that is essentially reaction of alcohols with themselves. So, you can have 2 alcohols that continue to react to form a polymer as well. So, some concepts here in the let's talk about the chain polymerization now. So, in this the polymer chain grows by reaction of a monomer with a reactive end group. So, there is some order to it rather than being random as it was the case in the previous example in the step polymerization. In chain polymerization there is some order to it, and I will explain how this order works. So, you may have an initiator molecule. That initiator molecule is highly reactive, and then that initiates the growth of these polymer chains. So, an initiator molecule represented by I here will react with a monomer to form an IO, this IO will then propagate further to continue to react, and the way the chain will grow is only in this uniform direction rather than any random combination of different reactants at that particular time. Typically such reactions, unlike step polymerization, there is no release of byproduct, and so the monomer is consumed slowly throughout the course of this reaction. So typical monomers, those that contain double bond, are very commonly used for chain polymerization. Also polymers that monomers that have rings in them can be used for chain polymerization, where the ring opens up and results in polymerization to occur, and we will discuss some examples as we go along. So chain polymerization, some general process. So generally there are 3 distinct kinetic steps. We already talked about initiation, where you have that initiator molecule reacting with a monomer. So this is an initiator. This generally results in generation of some free radicals or anions, cations, some other kind of complexes, which are essentially the active center. These are the reactive sites that are going to go find another monomer and react with it. So this is the initial phase, and this is obviously started. So if you want to start a chain polymerization, you will have to add a certain concentration of initiator to it, so that these initiation reactions can occur. The next is followed by a propagation. So once the initiation of the polymerization has already happened, propagation is nothing but these active centers reacting with the monomers and continuing to grow. So to again give you an example, the initiation in this case is, you have an initiator containing a free radical, which then reacts with, let us say here a C double bond C, resulting in a product which is combining that initiator with the molecule as well as another reactive site at the end of it. So this reactive site then can go with and react with another double bond to result in a larger molecule, and this will continue to propagate as time goes on. Here is the ring opening polymerization reaction. So you have another initiator B here, which is an anion, and it will go and react with this ring structure to give rise to a larger anion, which will again then find another ring structure, and this reaction will continue till the reactants are all consumed. So just as I discussed, this propagation will happen as we go along. So what about termination? So when does it typically stop? So it can stop when all the reactants are consumed, or there can be several other things that can happen. So this is combination. So it can happen that a one reactive site can, instead of reacting to the monomer, can react with another reactive site, and that will result in the loss of the reactive sites on 2 different molecules, and if enough combinations like this happen, all the reactive sites will be consumed. And another is sometimes disproportionation, where instead of actually having reacting, one of the active site takes up the electron from the another active site and does not really combine with the growing polymer, but still results in depletion of the reactive sites, resulting in loss of the polymerization. So this is called disproportionation. So typically both reactions take place, depends on what polymers you are using. Different polymers will result in different kinds of reactions. So for example, in polystyrene, mainly the termination happens through the combination. In PMMA, another polymer very widely used, it is typically disproportionation dominates at the temperature above 60 degrees Celsius. And then we have something called a living polymerization. So this is essentially, if the chain polymerization continue to go on and you still have reactive sites present, but it runs out of the monomers, then you will still have free radicals, the active centers that are available for the polymerization to occur, and this is something that we can then use to modify our polymers through different ways. So one thing we can do is that in this case, since the chain ends are reactive, we can then put another type of monomer which will then continue the reaction. So instead of having just a single type of monomer throughout the reaction, we can have 2 different types of monomer arranged in an order. So essentially we can synthesize block copolymers, because what will happen is you will have a molecule being generated here, which is I, let us say reacting with monomer 1 continue, and then let us say the monomer 1 finishes at this point, then if you add a monomer 2 to this reaction mixture with the active site already present, what will happen is this will then continue to react with monomer 2 and essentially result in a block copolymer, because you have a block of M1 here and a block of M2 here. So, that is how you can continue to do this. Typically you can continue to do this up to tri block copolymers. So, you can have another one monomer here M3 continuing to grow as the reaction is continuing. Typically by the time you are finished with 3 of these different types of monomers, there is enough combination or disproportionation termination that has happened that not many active sites are remaining. So, you do not get more than tri block copolymers by this method. So, just a couple of examples on ring opening polymerization. So, you can have a polymerization that starts from a cyclic monomer, and normally the ring is opened by some kind of acid or basis, and then the polymerization proceeds by chain growth reaction as we just discussed. Very commonly used with cationic and anionic initiators. So, some examples are polyesters, polyethylene oxide, polypropylene oxide, polycaprolactone and PDMS. All of them pretty much are very widely used for biological applications, and we will talk about most of these as we go along. Some of these terms you are going to become very familiar with in this course, and remember we are discussing all these polymers because we essentially want to build up some of the basic concepts of what different polymers are there that we can use for drug delivery applications and what are their properties. And once we have some basic knowledge of that, that will help us later in this course to then identify how can we modify them for different applications and requirements. So, here is a very common reaction. I mean this is a PLGA polymer which is very widely used in drug delivery applications, and the synthesis of this is through a ring opening polymerization where you have a lactide and a glycolide group that reacts in presence of an catalyst to give rise to a long polymer of PLGA. So, just between the comparison between the step and the chain polymerization, each has its own properties, advantages and disadvantages. So, typically for step polymerization the growth occurs throughout in a non-uniform manner. So, you can have monomers reacting with oligomers, forming polymers and all those kinds of things, whereas in chain reaction it is much more directional, where you will have an active site only reacting with the monomers. Degree of polymerization typically get with the chain reaction is low, and what I mean by that is it is difficult to get long polymers through step reaction, but with the chain reaction the degree of polymerization can be very high because you can add very less amount of initiator, and the reaction will continue to go on till all the monomer has been consumed. The monomer again is very rapidly consumed just because the reaction is happening at all monomer sites at once. In case of chain reaction the monomer consumption is much slower, but the molecular weight increases quite quickly as the chain grows. One advantage of the step reaction is that there is no need for initiator, it is a single reaction mechanism. Typically most of these initiators we talk about can be toxic because they are fairly reactive. However, in chain reaction you need an initiator to begin the reaction, and so subsequently for drug delivery applications when you talk about using these kinds of polymers you have to worry about if there is initiator contamination, non-reactive initiator present there and things like that. No termination step is required. This usually the termination occurs through the combination and the disproportionation we talked about. As the functional groups react you have less and less monomer and then the polymerization rate decreases. However, in this case initially there is increase in the polymerization rate because the initiator is creating more and more reactive sites, and then it reaches a relative constant rate till the monomer starts to deplete significantly. Okay, so we are going to talk about some basic properties of the polymers. So, the molecular weight is essentially the molar mass is the single most important parameter that characterizes a polymer or a macromolecule. We are going to talk about this throughout this course. Polydispersity essentially tells you what is the size distribution of the polymer molecules. So, let us say if I say polymer molecule is 100 kilodalton, that means that the average size of these polymer chains is 100 kilodaltons, but it does not mean that all of them will be 100 kilodalton. There will be some polymer chains which will be 110, there will be some which will be 90. So, this spread from 100 in this case essentially defines what polydispersity index is. The crystallinity and amorphousness, this affects a wide range of mechanical and optical properties. So, how crystalline or how amorphous the polymer is, and again all of this will be discussed in greater details as we go along. The melting temperature, which is again related to crystallinity, we are going to discuss. Glass transition temperature, this is related to amorphousness, we are going to discuss in the next class. And then of course, the degradability, how fast it degrades is very important, because that is going to essentially determine how fast the drug is releasing from this polymer, or how fast different properties are changing. And of course, for certain applications mechanical and electrical properties also become important. Let us say if you are going to use it in bone, you want it to be mechanically stable. If you are going to use it for neuron applications, you want it to be electrically conductive. So, some of those properties also become very important. So, so just quickly on the molecular weight, the molar mass of the polymer is essentially mass of 1 mole of the polymer as it is for any other molecule. So, essentially that means that what is the mass of an Avogadro number of molecules of the polymer. This is usually expressed in grams per mole or daltons. So, molecular weight of 100,000 daltons means the molar mass is this essentially 1 mole has about 100,000 gram of this polymer. So, for a homopolymer the mass is essentially nothing but the x times the mass of the monomer, where x is the total number of repeat units. And then the polymerization process inherently creates polymer molecules of different lengths. As I just said, you will not get all at a single molecular mass, they will all have a distribution. So, typically we always measure the average molecular mass, which is essentially nothing but the average degree of polymerization for these polymers. Okay. So, for this course we will stop here, we will talk about more about the molecular weight in subsequent classes, and discuss more about the properties of the polymer in the next couple of classes. Thank you.